In this section, we're going to learn about Stokes theorem. Stokes theorem is an extension of the circulation form of Green's theorem to three-dimensional space. It connects surface integrals to the curve around the surface, the boundary of the surface. All right, so let's read it together, then we'll try to interpret it. Let S be a piecewise smooth oriented surface with a boundary that is a simple closed curve C with positive orientation. If F is a continuously differentiable vector field over S, then the circulation of F around that boundary, okay, around C, is equal to the flux of the curl of the vector field through the surface. All right? So let's try to interpret this. We have some nice piecewise smooth surface S, and then the boundary of that surface is C. Okay. Now, so the boundary of the surface right here is C, but the surface itself is S. Okay. Now, in order to make this work, we have to make sure that there is some sort of relationship in terms of the orientation between our surface S and our and the boundary C. Okay, we call this relationship positive orientation. The idea here is that we want, if we're walking along C, we're walking along the boundary curve C, with our head in the direction of the surface normals of the surface S. So surface normals of surface S are going to go upward in this case. Okay, so that's how surface S is oriented. Okay, so we're walking along in this direction with the head in the direction of the normal, upward in this case. If we're walking along in that direction, then our left hand should be pointed towards the surface. Our right hand should be pointed away from the surface. If in that case, then we have positive orientation and Stokes theorem holds. Okay? All right, so what is Stokes theorem saying? So the actual idea is fairly straightforward. We have the curl of F. Okay, so imagine that this surface exists in the context of some vector field. I'm not going to draw the vector field except maybe in a few places, so the drawing doesn't look too busy, but it's in the context of some vector field. A vector field is flowing through this surface. Okay? Now, what we want to know is we want to know the curl of F at the surface, but we want to know only how that curl is affecting the surface. All right, so I could have, I'm not going to draw it. Let's draw the gradient of the vector field. I'm sorry, the curl of the vector field. Okay, so maybe the curl of F is pointing in this direction. Okay, that means that the original vector field is circulating around the curl at that point. Okay, according to the right-hand rule. Okay, this the curl of F points in the direction of the axis of rotation. Right, but not all that rotation is relevant to the surface. We only care about the part of the curl relevant to the surface. So what we do is we take the dot product. Remember, when we're thinking about the this vector surface integral. That dot ds means we're dotting it with the unit normal vector, normal to the surface, integrated over the surface, right? So we're asking how much of the curl of f is in the direction of the normal vector. Okay, how much of the curl of f is in the direction of the normal vector? So I could break into two components. This component here is the amount of the curl that's in the direction of the normal vector, the component of the curl in the direction of the normal vector. Okay, and so that tells me the amount of circulation of the vector field that is tangent to the surface. Okay, now imagine that we do this for every point. Kind of break it into boxes like we have in the past. It's a little thin. Yeah, okay, that'll do. Okay, if we take the curl of f, the dot product of the curl of f and the normal vector, it will tell us the amount of circulation parallel to the surface in each one of these little boxes, right? We're discretizing it. So we get the curl in every single box. And just like before, adjacent parts of the surface, adjacent cells here, the components of the curl will cancel out. So we'll get adjacent parts that cancel out. So for example, these two right here, we're measuring the circulation on this edge. We measure it in this direction, but because we're integrating, we're going to also add it to this direction. But if we're measuring the circulation in this direction, it'll be one sign. It's the same thing here, but just the opposite sign because we're measuring it in the opposite direction. Just like for Green's theorem. So they'll cancel out. Okay? These will cancel out. These will cancel out. Anytime we have adjacent cells, they'll cancel out. This one up here will cancel out because if you go to the other side of the surface, the part that we didn't draw, there's another cell there that'll cancel out. Okay? The only part that won't cancel out is when we do not have an adjacent cell. Which means when we get to the boundary of the surface. Okay, so the only ones that aren't being canceled out are the ones right up against the boundary of the surface. That one, that one, that one, that one. Okay. And if we take all of those together, they're moving us in this direction. We're circulating along the boundary of the surface. And so taking the portion of the curl, the flux of the curl through the surface is the same as calculating the circulation around the boundary of the surface. Okay? So let's take a look at an example. Here, let's let f be the vector field with components negative yz, xz, and xy. We're going to use Stokes' theorem to evaluate the flux of the curl of that vector field through surface S, where if surface S is the part of the paraboloid z equals 15 minus x squared minus y squared that lies above the plane z equals 11, oriented upwards. Okay? So, let's get a sense of our surface and what we're dealing with here. So we have a paraboloid, 15 minus x squared minus y squared. That is a paraboloid that opens downward with its vertex up at z equals 15. Let's put z equals 15 somewhere up here. Okay, we have a parabola that opens down, or a paraboloid rather, that opens down. And then somewhere at 11, maybe right here, we stop. It's above z equals 11. Okay? All right, and we want the flux of our vector field through this surface where we're going to orient the surface upward. So surface normals would be going upward. Okay? Now, we could calculate that directly, or at least we could try to. We know how to do surface integrals. We know how to take the curl of a vector field. Okay? But instead, we notice that this boundary here, it's really quite a nice shape. It's a circle, right? If we just slice, let me make it a little smaller. There we go, that's a little better. If we slice the paraboloid horizontally through z equals 11, we'll end up with a circular cross section. That's the boundary. Circles are pretty nice to integrate over. We've got polar coordinates, okay? So maybe that's the way we should go here. Instead of integrating the flux of the curl through the surface, maybe we should integrate the circulation of the vector field over that boundary. Okay? So if we're going to do that, we're going to need a parameterization for the boundary. Okay, so our boundary here at z equals 11, it's going to be this this paraboloid, but at z equals 11. So let's grab that boundary. So the paraboloid is 15 minus x squared minus y squared, and we're looking at the boundary when z is equal to 11. So if I move the x squared and the y squared to the left-hand side of the equation, the 11 to the right-hand side, we see we get a circle of radius 4. And so I can parameterize that. I'm sorry, a circle of radius 2. I could parameterize that with 2, x equals 2 cosine t, y equals 2 sine t. We've parameterized circles lots of times before. Okay? And so integrating the circulation, we're just going to integrate the function evaluated at our parameterization. And I'm going to take the dot product with the derivative of that parameterization. Okay, just using the formula for evaluating a vector line integral. Okay, so we've got our parameterization here. I do need r prime. R prime of t is going to be negative 2 sine t, 2 cosine t. And I want to go all the way around the circle, so my limits will be from 0 to 2 pi. Okay, so let's plug in. Let's see what we get here. So f of r of t. Now my x is, oh, and I forgot the z component. Very important here. It's not just a circle in 2 dimensions. It's a circle in 3 dimensions, right? The z is just 11. The z value of this circular cross section here, it stays at a constant height of z equals 11, right? And so the derivative would be 0. Okay? All right. And one more thing before we plug in. Good thing to check that we have the right orientation. We know we want the surface normals oriented outward. A quick check, just plug in a couple points. You'll be able to see that this does move counterclockwise in the xy plane. Okay? So the parameterization we have will move the correct direction. We would be positively oriented. Right? If we weren't, we could still use this, but we just have to change our sign and throw a negative in front because our answer would be the negative of what we want. Okay. So let's plug in our vector valued function into our vector field. So f is negative yz, xz, xy. Okay, so negative yz, so this and this, negative 2 sine t times 11, xz, so this and this, 2 cosine t times 11, and then xy, so this times this. So 2 cosine t times 2 sine t, that's 4 cosine t sine t. And with that, so that's our vector field evaluated along our parameterized boundary, our parameterized curve. Okay? And then I'm going to take the dot product with our prime of t, which is just this right here. Okay? I'm running out of room here, so add it in over here. What is it? Negative 2 sine t, 2 cosine t, 0. Negative 2 sine t, comma 2 cosine t, comma 0. Integrated with respect to t. And if we take the dot product, we would get negative 2 times negative 2 times sine t times sine t times 11. So that's going to be what? 44 sine squared t. Multiply second components, I get 44 cosine squared t. And then this times 0 is just 0. So factor out the 44. Sine squared plus cosine squared is going to be 1, so I'll just get the integral of 44. And it's almost trivial at this point. You know what? Why don't we go ahead and finish it off? If I integrate with respect to t, I get 44t. I'm going to evaluate that from 0 to 2 pi. And so I get 44 times 2 pi, or 88 pi. That is the final answer. Okay? We did it using Stokes Theorem. Instead of calculating the surface integral directly, we opted for using the circulation around the boundary of the surface. And that made the problem probably quite a bit easier. Let's take a look at one more example. In this example, we're going to be using Stokes Theorem again, but we'll kind of be using it in the opposite way. The last problem, we started with a surface integral and used Stokes Theorem to change it into integral over a closed curve. In this example, we're going to do it the opposite way. We're going to start with an integral over a closed curve and turn it into an easier integral over a surface. So we have our vector field f. We want to use Stokes Theorem to evaluate the circulation of the vector field f over curve C, where C is the triangle with these 3 vertices, 10, 0, 0, 0, 10, 0, and 0, 0, 10, oriented counterclockwise as viewed from above. Okay, so let's start by just drawing out what we're dealing with here. x, y, z. So we have three vertices, 10, 0, 0. So let's put 10 right here. 10, 0, 0. 0, 10, 0. So we'll go out 10 on the y-axis. And 0, 0, 10. So we'll go out 10, 10 on the z-axis. Okay? And we're going to integrate this function, this vector field, over the curve. That connects those 3 points over that triangle. Okay? And it's going to be oriented counterclockwise as viewed from above. So if I'm looking above, looking down the positive z-axis, it would be oriented counterclockwise. Okay? So that means we would be going this way. We're already kind of looking at it from above, right? The way I've drawn it, it's kind of from above. We have more of an above or perspective of it. Okay. Now, calculating this as a line integral, a little bit annoying because we kind of have to break it into 3 pieces, right? Each one of these sides would have to be handled separately as its own line integral. I prefer not to do 3 line integrals, so we can use Stokes' theorem to instead integrate over a surface that has these 3 edges as its sides, right? As the edge of the surface. So according to Stokes' theorem, I could change from the integral over a closed curve, circulation over a closed curve, to an integral, a surface integral, over a surface where that closed curve is its boundary. And I'm going to instead find the flux of the curl of the vector field through the surface. Okay? Now, in order to do this, we need to choose a surface. Now, one of the interesting things about Stokes' theorem is it actually doesn't matter which surface you choose so long as the boundary is the curve that we started with. Okay? So, for example, I could kind of construct a pyramid. If you can imagine that point coming out towards you, I can construct a pyramid and then integrate over the surface of the pyramid. Of course, that seems like a lot of work, right? Any surface will work. So since any surface will work, let's take the easiest possible surface. We can take the plane in between these 3 points. 3 points determine a plane, so I know there is a plane there. Okay? So that's going to be what we're going to do. We're going to integrate over the surface where the surface is the plane. Okay? So the very first thing I need to know, I need to find out what's the equation of this plane. Okay? To find the equation of a plane, I need a point on the plane. I have 3 of them, right? And I need a vector normal to the plane. Okay, so to find that vector normal to the plane, let's find 2 vectors parallel to the plane. So I could find this vector here, for example, and maybe this, well, maybe we'll do it this way. This vector here, any 2 vectors will work here, and then take the cross product to find the normal. Okay, so let's see, vector 1, let's end at the y point and start at the x, so n minus start. I get negative 10, 10, 0. And v2 will end at the z point, the point on the z-axis, and start at the point on the x-axis. And so I get -10, 0, 10. I'm going to take the cross product of those. So I'm going to take the cross product of -10, 10, 0 with -10, 0, 10 to find a vector normal to my plane. First component, I get 100. Second component, I get -100, but it's the j, so I throw in another negative in front, it's 100 again. And for the k component, I get 100 again. So 100, 100, 100, that is normal to the plane. Now remember, any vector that is a scalar multiple of this would also be normal to the plane. 100, 100, 100 is kind of big. I'm going to divide everything by 100. 1, 1, 1 would work just fine. Okay? Just a scalar multiple. And so the equation of the plane is 1 times x minus 10 plus y plus z equals 0. Using 1, 1, 1 as the coefficients, and then using the point -10, 0, 0 as the point on the plane. Okay? Now I need to find a parameterization for the surface. Okay, so to find a parameterization for the surface, I'm going to solve for z. So if I subtract everything, I get -x minus y plus 10. So let's write it this way, 10 minus x minus y. Okay? And then I could parameterize the surface by taking RUV equals, I'm going to set x equal to u, y equal to v, and then z would be 10 minus u minus v. Okay? So we know how to calculate this surface integral. We're going to parameterize it like we just did. I'm going to take the gradient of f, I'm sorry, the curl of f. I'm going to evaluate it on our parameterization. And then I'm going to take the dot product of that with the cross product of the partial derivatives of our parameterization. Okay? So I've got a couple cross products to find here before I can plug in. I need the cross product of my vector field, into which I will plug in my parameterized surface. Okay? And I also need the cross product of the partial derivatives of my parameterization. Let's start with that. We've already found our parameterization. Let's take our partial derivatives. So I get what? 1, 0, -1. And partial derivative of r with respect to v would be 0, 1, -1. Let's take the cross products. So I get 1, 0, -1, and 0, 1, -1. And if I take the cross product for the I component, I would get 1. For the j component, also 1, taking into account that extra negative in front. And for k, also 1. That probably shouldn't be surprising, right? That we get 1, 1, 1. We have a plane. The normal to the plane is 1, 1, 1, right? Remember, this is going to be normal to the surface. That is what it gives us, okay? A normal to the surface. we should make sure that we are oriented correctly. Remember, Stokes theorem only works if we have a certain orientation. Now we want the outer boundary to be oriented counterclockwise. So that means we want the normals to the surface to be coming, it's kind of hard to draw, but coming towards us. Okay, coming towards us. Yeah, I don't know if I could draw it well, but we want it coming out of the screen, out towards your face. Okay. 111 is pointing exactly the direction we want it to go. If it's not, then our answer will just be the negative of what we want. So if our orientation is wrong, no reason to panic. Just throw a negative in front and it will correct for the wrong orientation. All right. In this case, the orientation is correct. The normal we're getting is the way we want it to be, okay, for Stokes theorem to work. All right. So we have this. That's just going to be 111. We need the cross product of our vector field. Here's our vector field up here. Let's go off to the side here. Starting to run out of room to write all this stuff. Okay, so I need the curl of the vector field. So that'd be the curl of 2x plus y squared, 9y plus z squared, 8z plus x squared. Okay, so that means I, j, k. The first vector is the vector of partial derivatives operators, partial x, partial y, partial z. And then the last row is the components of the vector field, 2x plus y squared, 9y plus z squared, 8z plus x squared. Okay. For I want partial derivative of this with respect to y. That's 0. Minus partial derivative of this with respect to z. That's 2z. So I'm going to get negative 2z for the first component. Okay. For j, partial derivative of this with respect to x, that's 2x. Minus partial derivative of this with respect to z, that's 0. So I get 2x, but then it's the j component, so I get another negative, so it's going to be negative 2x. And then for the k component, partial derivative of this with respect to x, that's 0. Partial derivative of this with respect to y, that's 2y. So negative 2y all said and done. Okay. Okay, so that's the curl of our vector field f. Now what we want to do is we want to plug in our particular parameterization. So let's leave the region of integration abstract for now. So if I plug in my my parameterized surface, so what do I have? Negative 2z, negative 2x, negative 2y. So into z, I plug in 10 minus u minus v. X is u, y is v. Okay. Negative 2z, so that's going to be negative 2 times 10 minus u minus v. Negative 2x is negative 2u. Negative 2y is negative 2v. So I take the dot product of that with the cross product of my partial derivatives, and those partial derivatives, that cross product, was just 111. Okay, so if I take that dot product, I'm going to just have negative 2, 10 minus u minus v. Oh, this is going to be quite nice. Minus 2u minus 2v. Okay, now let's find those limits of integration. Now I want to know the bounds of u and v, but because u and v were just the x and y, where was it? U was x, v was y. If I could find the bounds for x and y, then I also know the bounds for u and v. So what I want to do is I want to take a look at this from above so I could focus on just x and y. Let me grab this. We'll move it over here so I have room to work on it. Okay. So I'm going to look down at it from above. If I look down at it from above, I'd still go have this point and this point, but this point will look like it's just at the origin. Okay, so this is, I don't know, both the XY space, but also the UV space. Okay, so this is what it looks like from above. So I could slice it up in either the X direction, the U direction, or the V direction. I'll slice it up in the V direction, which means I'd be integrating first with respect to V and letting the u be fixed. So if I slice it up in that direction, that means each slice starts at v equals 0, and it ends along this line here. Now this line's pretty easy to calculate. The equation of this line up here is, let's use the variables we've chosen, v in place of y. The slope is, I'm going down 10, then over 10, so it's negative 10 over 10, which simplifies to negative 1. So negative 1, u in place of x, plus the intercept, which is 10. Okay, so v equals negative u plus 10. So if I'm integrating with respect to v first, I'm going from v equals 0 to v equals negative u plus 10. And then collapse that dimension. You would be going from 0 to 10. So you would go from 0 to 10. And I won't evaluate the integral all the way, but I will take one more step here to simplify the integrand. If we distribute that negative 2, I get negative 20 plus 2u plus 2v, and then minus 2u minus 2v. So the 2u cancels with the 2u, the 2v cancels with the 2v. And so I just have a very straightforward, very simple double integral. Okay? So hopefully that process made sense. So sometimes Stokes' theorem is great. We're taking a surface integral and re-expressing it as an integral over the circulation of the boundary of the surface. But sometimes, like in this example, Stokes' theorem is great for taking the integral over the circulation of a curve, of a closed curve, and changing it into the integral, changing it into a surface integral. Okay? This surface integral took a little work to get set up, but it's much easier to evaluate this surface integral than it would be to evaluate this integral over all three sides of the circulation. Okay, all three sides of the boundary.